Section 6.2, Polynomials and Linear Factors. Our objectives are to analyze the factored form of a polynomial and to write a polynomial function from its zeros. Just as you can rewrite a whole number as a product of its prime factors, you can write a polynomial as a product of its linear factors. So just to look at our whole number, let's say we have the number 6. If I use my factor tree and factor this becomes 2 and 3, and those don't factor anymore, so those are prime numbers, which are numbers divisible by 1 in itself. So the way that we can write this is as 2 times 3 is equal to 6 as the product of its prime factors. Well, the same thing can happen for a polynomial equation. So remember, polynomial equations have variables in them normally, so this would be x squared plus 4x minus 12. So if this is our polynomial equation, then I can factor this into x plus 6 times x minus 2, and this right here, if we multiply it together by foiling or boxing, we would get our original equation, and these are called linear factors because the degree of each of these binomial terms separately is a degree 1. So because the degree of each binomial factor is 1. So things that are linear cannot be factored any further. A linear factor is similar to a prime number in that it cannot be factored any further. Once a polynomial has been completely factored to its linear factor, it is in factored form. So the first thing we're going to practice is writing a polynomial in factored form. So for the first one, remember we always look for our greatest common factor. And in this first equation we have, notice 2 goes into each of them, and also we have an x that can go into each of our factors. So 2x would be the greatest common factor, and then this becomes x squared plus 5x plus 6. And then when we have 3 terms, we look to see if we can factor it further by setting up 2 sets of parentheses. So factors of 6 that add up to 5 are x plus 2 and x plus 3. This would be my polynomial in factored form. And then if you look at for b, you do the same thing. Look for a greatest common factor, which would be 3x, and then that becomes x squared minus x minus 12. And then of course we can factor the trinomial further by doing x minus 4 and x plus 3. And then this would be the product of linear factors because it cannot be factored any further and each term is linear. The next thing we want to talk about is the relative max or minimum. Remember your relative max or minimum value, well, we talked about the maximum or minimum value, but the relative max or min, if you look at this graph right here, this point right here would be called what's the relative, or sometimes relative is also called local maximum. And the reason we say relative is because relative to the points around it, it is the highest point on the graph. However, if you notice the arrow on the other side right here, this graph is going up to infinity. So because of it, it's not the actual highest point on our graph. And again, sometimes people call those relative or local maximum. So this point right here would be called a relative or local minimum, because relative to the points around it, it's the lowest point. However, our graph does go down to negative infinity because of the arrow right there. So because of that, it's not the actual lowest point in our graph. Unlike when we talked about our quadratic equations, remember the quadratic equations make a parabola shape. So for these, this point right here is just called the minimum value, or sometimes we call it absolute minimum because there are no points on the graph lower than it. Now, if you look at this graph, I can see 1, 2, 3 x-intercepts. So x-intercepts, so there's 3 x-intercepts. And x-intercepts are also called the zeros of the graph. Why are they called the zeros of the graph? Because it's when you set your equation y equal to 0, that's how you get your x-intercept. Another name for zeros is sometimes called roots of the equations, because when we were solving quadratic equations, remember we had to take the roots of both sides to sometimes solve. And they're also called the solutions. So if you see x-intercept, zeros, roots, or solutions, it kind of all means the same thing. Also remember that your relative max or relative min value is always usually the y value of your coordinate ordered pair, but when we're graphing these, we're going to need both the x and the y. All right, so for the next part, we're going to talk about factors and the zeros of a polynomial function. Find the zeros given this equation and then graph the function. If I look at this equation and I want to find the zeros, remember that means I really want to find the x-intercepts. Well, how do you find the x-intercepts? You set the equation equal to 0 first, and then you're going to solve for x. If the equation is not in factored form, that's the first thing you're going to want to do. But since this is already in factored form, it's easy to find what the x-intercepts are going to be, or the zeros, because I can just set each binomial equal to 0, because if one binomial is equal to 0, then the rest of them, 0 times anything, would be 0. And so when I solve here, I get x is equal to 2. This one is x is equal to -1. And here, x is equal to -3. So if I'm graphing that, this is the first thing I'm going to find are my x-intercepts and put those on my graph. So I have an x value of 2, -3, and -1. Now, after I do that, because this is not quadratic, we don't really know what this shape is going to look like until we graph it in our calculator. So that's the next step that I'm going to do. I'm going to get out my graphing calculator, and then I'm going to plug the equation into my y equals. And notice I plugged it in exactly how it is seen on your paper. And when I'm graphing this, then the next thing that I want to do, so after you plug it into your y equals, then we're going to just hit zoom 6 to look at a standard window from x values -10 to 10. Notice that if I look here, this looks like it's at, I can check my zeros by doing second trace value. So if I do -3, I should get a y value of 0, which I do. Also -1, and also the if I plug in an x value of 2, you'd notice that it would be on the x-axis as well, because there's your x-intercepts. Another thing to find that's nice is your y-intercept. So remember, how do you find your y-intercept? You plug 0 in for x and solve. So my y-intercept would be at -6. So the y-intercept is 0, -6. So I'm also going to graph that. Notice that I have a relative max and min, and so I want to find those values on my graph. So to do that, I do second trace. Notice that you have minimum and maximum values. So let's do number 4 first, because that's the first one that we see in our graph. So if I hit that, I'm going to scroll using my left and right arrows over as close as I can to this point here. If we want something to the left of that point, something to the left would be somewhere over here on my curve. Enter. It doesn't really matter exactly where you hit it. And then to the right of that point where we think the maximum is would be somewhere over here. Enter. Notice that those two arrows right here and here are pointing towards each other, and in the middle is where you think your maximum is. So just hit enter for guess, and we get a relative maximum value. And I'm going to write down the x and the y just so that I can graph it in a second. So that would be the point. And then I'm going to do the same thing, except for now I want the other point, which is the relative min. So second trace, now I have to do minimum, and then use my right arrow to scroll over. Something to the left of that minimum would be on this side, something to the right on the other side. Enter, oops, enter. And then that would give me my relative minimum. So, and again, round to the nearest hundredth, so 0.79 comma -8.21. And I'm going to use that to help me graph, and I'm going to copy this onto my paper. Now that I have this copied, I can go ahead and draw the rest of my graph in. So I'm going to put my y-intercept 0, 1, 2, 3, 4, 5, 6, negative would be right here. Now, because the points aren't very nice for my relative max and relative min, you're just going to kind of estimate where you think they should go. So -1, 2, and then 1, 2, 3, 4. So somewhere around here would be my relative max. And then 0.79 is less than 1, and then down 1, 2, 3, 4, 5, 6, 7, 8 would be somewhere in here. And then if you have your x-intercept, your y-intercept, and your relative max and min, then all you have to do is kind of just trace the curve in. And make it look like, you know, the graph that's on your calculator. So use that kind of as a guide to help you when you're graphing these. And of course, if you want to pick out other values on your calculator, you can by going to your table, so second graph, and you can pick out other values if you think that's going to help you graph it even better. So if I look back at my graph though, this graph looks like the graph that I graphed, so that I know I'm done. Now, you can reverse this process and write the linear factors when you know the zeros of your equation. So from here, we found the zeros. Now, if I know these zeros, I can go backwards and write the equation, is what that's saying. So we can do this by using the factor theorem. The expression x minus a is a linear factor of a polynomial if and only if the value of a is a zero of the related polynomial function. So if we go back to the last problem that we did, notice that our a values would be the 2, the -1, and the -3. So if I go backwards, x minus -3 is where I get x plus 3, x minus -1 is where I get x plus 1, and x minus 2 is where I get x minus 2 for my original equation. So for these examples, we want to write a polynomial function in standard form with the given zeros. If I have these for my zeros, the first thing I want to do is write them as linear factors. So this would be x minus my 0, so x minus -2. This one, for the next one, would be x minus 3. And x minus 3, we have 2 of them. So really, remember, this is x plus 2, x minus 3, and x minus 3. You can check it by setting equal to 0 and solving. You should get -2, 3, and 3. Now, if I want to write this in standard form, that means that I have to multiply this out and combine like terms. So I'm going to FOIL these out first. When I FOIL those out, I get x squared minus 3x plus 2x minus 6. I have to combine like terms. So this would be x squared minus x minus 6. And I'm not done because now I need to multiply this trinomial times this binomial. So when I do that, I'm multiplying the x times this term here and this term here. So that gives me x cubed minus 3x squared. And now I'm going to take the next term, which would be the negative x, and multiply it by the x and then the -3. So when I do that, I get minus x squared plus 3x, and then I have the last term, which is the -6 times the x and -6 times -3. So minus 6x and then plus 18, and then all I have to do is combine like terms. So I get y equals x cubed minus 4x squared and then minus 3x plus 18. And that would be my equation in standard form with the given zeros of -2, 3, and 3. So if I wanted to, I could plug this equation that I just found into my graphing calculator and check to see, does it have the zeros of -2, 3, and 3? And of course, you would see that it does. So why don't you guys pause the video and see if you can do B on your own, and then unpause it and we'll do it together. So for B, again, you're going to want to first write these as linear factors. So this would be x plus 4, x plus 2, and x minus 0, which is just x. You don't really need to write the minus 0. So then I need to FOIL this out. So when I FOIL it, I get x squared plus 2x plus 4x plus 8 all times x. So this gives me, I'm going to write the x in front, x times x squared plus 6x plus 8. And then I just have to distribute. So x cubed plus, so x cubed plus 6x squared plus 8x. And if I make that y equals, this right here is my new equation. So if I plug this into my calculator and find the zeros, I would notice that x equals -4, -2, and 0 would be the zeros of my equation. If we look at this last example right here, it says we are given these zeros and we want to write something with a degree 5. So if I'm giving these zeros, the first thing I want to do is write them as linear factors. So this would be x minus 1/3 times x minus 5, and x minus -2 would be plus 2. Now, if I were to multiply this out, I know that I can tell that x times x times x would be x to the 3rd power. So I'm not going to have a degree of 5. So that means I need to change around some of the exponents in this equation. Now, most of the time we don't leave our linear factors like this. Just like when we learned how to factor, I would take that 3 and put it in front. So 3x minus 1 still gives me a 0 if I solve it. Still gives me a 0 of x is equal to 1/3. It's just written in a different form. So right now we have, if we multiply this out and put it in standard form, a degree of 3. So that means I need 2 more. So if I change around the exponents, that would help. If I make this a 3, then I would have 3x times x times x times x times x 3 times. So that would be a degree of 5. Or I could, instead of doing that, I could maybe make change it around a little bit and do this as 2, 2, and 1, because then I would get 2 plus 2 plus 1 would be 5. So that would also work. So there's many different variations for this. And then if you wanted to put it in standard form, of course, you would have to multiply it out. But I'm going to skip that for right now. So this is one possibility. And as I said, if I had 3x minus 1, maybe if I made this one cubed times x minus 5 times x plus 2, that would also be another possibility that we could have, because just because I'm changing the exponents doesn't mean that I'm changing the zeros by changing the degree of each of the binomials. That doesn't really affect it. So for the next part, we want to find the multiplicity of a 0. If a linear factor of a polynomial is repeated, then its 0 is repeated. A repeated 0 is a multiple 0. A multiple 0 has a multiplicity equal to the number of times it occurs. So for these examples, it says find the zeros of the function and state the multiplicity of each 0, and then state the degree. Now, the zeros are easy to find. Remember, to find the zeros, we said each binomial equal to 0 and solve. Well, we don't really need the degrees in this, because if you were to solve 0 equals x minus 5 to the 3rd power, well, you would take the cube root of both sides, but the cube root of 0 is 0, so that doesn't change my equation, which is why I don't need to enter that when I'm finding my zeros. So this binomial right here, when I solve, I would get a 0 of x equals 5. For the next one, I get 1, and the next one would be -1. Now, for this, to find the multiplicity of the 0, you look at how many times it occurs. So this right here means I have x minus 5 times x minus 5 times x minus 5 3 times. So since it occurs 3 times, I would say that 5 has a multiplicity of 3. Notice that this one is to the 1st power, so we don't say that 1 has a multiplicity of 1, so I'll skip that. I don't even write it down. And the next one would be the -1 right here. It has a degree of 2, so then I would say that -1 has a multiplicity of 2. Now, to find the degree of a polynomial equation, remember that your equation has to be in standard form. So we don't really need to multiply this all out. You can look at your numbers here, here, and here to see what the degree is going to be. If I were to multiply this out, notice I would have x 3 times because of that 3, so it would be x times x times x, and then times another x for this one right here, and then I have 2 more for this one. So if I multiply that out, I would have 1, 2, 3, 4, 5, 6, x to the 6th power. So that means the degree of the function is 6, because if I were to put it in standard form, the highest term would be of a power of 6. So then for b, see if you can do the zeros on your own, and then unpause it and check your answer. So for b, I have 0 is equal to 2x, 0 equals x minus 2, and 0 equals 2x plus 1. So for the first one, divide by 2 and you get x is equal to 0. Here you get x is equal to 2, and this one, if you subtract the 1 and divide by 2, you get x is equal to -1/2. So those are the zeros. The multiplicity then, 0 has a multiplicity of 1, which we don't write. X equals 2 has a multiplicity of 3 because of this power right here. So 2 has a multiplicity of 3. And then negative a half has a multiplicity of 4. So negative 1/2 has a multiplicity of 4. And yes, you do need to specify what is what, because otherwise I wouldn't know what has a multiplicity in your equation. Now, if we were to multiply this out and put it in standard form, notice I would have 2x, and then I would have times an x that occurs 3 times. And then this one occurs 4 times, so I'd have times 2x 4 times. And if I do that out, I get 32x to the 1, 2, 3, 4, 5, 6, 7, 8. So that means the degree of this would be a degree of 8. Next, we're going to find any multiple zeros of the given function. Now, if you're giving your function in standard form, then the first thing you have to do to find the zeros is to factor your equation. If we look at a here, you would need to factor out a greatest common factor, which would be x squared, and then you would get x squared plus 6x plus 8, and then of course that trinomial factors further. So it factors into x plus 4 times x plus 2. If I want to look at my zeros, remember you set the equation equal to 0, so you would have 0 equals x squared, 0 equals x plus 4, and 0 equals x plus 2. So when you solve, you get, take the square root of both sides for the first one. Square root of 0 is just 0, so plus or minus 0 doesn't change anything when you do that, so x is equal to 0 here. Here, x is equal to negative 4. And here, x is equal to negative 2. So because of this square right here, I know that 0 is actually what we call a multiplicity of 2. So x equals 0 is a multiple of 2 for the multiplicity. The other ones don't have a multiplicity because they don't have any other powers. If you look at b, we can factor out an x. So when we factor out x, we get x times x squared minus 4x plus 4. And then you can factor that further to x minus 2 times x minus 2. And for this one, now if we set it equal to 0 and solve for the zeros, we get x equals 0, and then x minus 2 and x minus 2 equals 0, which since they're the same, we only need to write it once, so x is equal to 2. And which one has a multiple 0? It would be x minus 2, which is a 0 of 2. So 2 has a multiplicity of 2 because there are 2 of them in our answer. For the last one, this one's nice because it's already in factored form, so I don't have to factor it. So when I solve for my zeros, I get 0 equals x minus 2, 0 equals x plus 1, and 0 equals x plus 1 again, and this one's squared. Really, I can write this as x plus 1 cubed since I have 3 of them. So this gives me x is equal to 2, and this one gives me x is equal to negative 1. And notice because I can write it like this 3 times, negative 1 is a multiplicity of, then we say 3. The next part is I want to talk about equivalent statements about polynomials, which we've already said before. Now, if this was our equation right here, we had y equals x squared plus 3x minus 4. Well, if you want to find the solutions to your equation, you set the equation equal to 0 and solve. So I know that if I were to solve this, I would have y equals, and we could do x squared plus 3x minus 4. So x in this case would be plus 4, and x minus 1 is how that would factor. And so this would be x is equal to negative 4, and x is equal to 1. So we're just looking at the negative 4 part for right now. So I say that negative 4 is called a solution of the equation when you set it equal to 0, because that's one of the answers that you get. Negative 4 is also what we call an x-intercept of the graph. So if you were to graph this and put in your y equal, you would see it would cross there. I would also say that 1 is the solution of the equation, and 1 is also x-intercept of the graph. So negative 4 is a 0 of the equation. It's just another term instead of saying x-intercept or solution. And x plus 4 is what we call the linear factor. So those are terms that you should know. We could also say that negative 4 is a root. So that just means the same thing, all those terms that we have right there. Now for the very last example, it says given the graph to the right, we want to write an equation in factored form. So if you want to write an equation in factored form, the first thing you want to do is find your x-intercepts on your graph. So we have one here, here, and here. So that means the solutions, or the x-intercepts, or the roots, or whatever you want to say, they all mean the same thing, are x equals -7, -3, and 2. When I have this, then the second step would be to write the equation as linear factors. So I'm going to have y equals, and I also have to take into account some a value, just like when we had vertex form for y equals a times x minus h quantity squared plus k. Remember, we had to find the vertex, and then we also had to find this a value in our equation by picking a point and plugging it in and solving. So it's the kind of same concept when you're doing these polynomial equations. You need to remember to put an a value in front so that you can figure out what that is by picking a point on your curve. So x minus -7 becomes x plus 7 as a linear factor, x plus 3, and x minus 2. So now I need to find that a value. So the question is, how do I do that? I'm going to pick any point on my graph as long as it's not an x-intercept. So cannot be an x-intercept. The easiest one to usually pick is your y-intercept because it gives you an x value of 0. So you can pick the y-intercept as long as it is not also an x-intercept. So I'm going to use this point right here. Now, do I have to use this point right here? No. I can really use any other point on my curve. I could use the point here, I could use the point over here, and I would pick something that's nice. So 0, -4 is what I'm going to use. So I'm plugging in -4 for y, I'm solving for a, and I'm plugging 0 in for x. You notice that this is why it's really nice, because we can just get rid of those right away. So -4 equals a times 7 times 3 times -2, and 7 times 3 times -2 gives me -42, and of course we write the number in front of the variable, and now we're trying to solve for a, so a is equal to -4 over -42, which is really 2 over 21. So this is what I'm going to use for my a value. So then my equation would be y equals 2 over 21 times x plus 7 times x plus 3 times x minus 2, and then you could plug it into your y equals to see that your graph looks similar to this graph. It might not be quite exact because I graphed it by hand, but it should look similar to this. Now, if I wanted to write this in standard form, so if need standard form, what would I have to do? I would have to multiply this all out and combine like terms. So if need standard form, multiply equation by foiling, or you can use the box method and combine like terms. So make sure that you know how to do each of these different methods that we have here. So again, we need to be able to write an equation by factoring it, find the zeros, find the multiplicity of zeros. We need to be able to, given zeros, write an equation, be able to write it in standard form, find the degree of our equation, and also from the graph be able to write the equation. And so make sure you have all this with you for class tomorrow.